is a chapter 2 test. Ignore these equations. I know they're there and I didn't erase them, but they won't come up in the real test, so I have eliminated them from the test here. Of course, pause every time and read through the information. I won't be reading you everything. I figure you can read. Here's a graph of concentrations changing. Well, the reactants start at some amount and then they reduce at a certain rate, don't they? The products obviously start at 0 and increase at a certain rate. Well, if we take this amount and say we'll double it about that amount, I think, which means that D is 3 times that of C. So in the same amount of time, it has increased from 0 to be 3 times the amount. It's increasing at 3 times the rate. The rate of increase of D will be 3 times the rate of C. The appearance of D will be 3 times the rate of the appearance of C. We get the same numbers for the concentrations of B, that's a faint line, but B and A, they correspond. So they have reduced effectively to 0. I'm going to assume that comes out to there. Otherwise, I don't know what to do. If A and B start at 3 times the amount and yet arrive at effectively 0 at about the same time, then A has been reducing, disappearing, at the 3 times the rate that of B. So the disappearance of A is 3 times that of B. You will take 3 A's used up for every 1 B. Now we have an equation, don't we? Now, remember though, the concentration could have been something else. It could have been, A could have been here or something, and also then been used up at 3 times the rate. That would be very hard to eyeball, and without numbers, hard, specific numbers, that would be very difficult to use. So what do we know? We know that equation, and A is at 3 times the concentration and reduces or disappears at 3 times the rate. D is produced at 3 times the rate of C. That's all the things that I could think of to say for number 1. On number 2, the appearance of ozone is 2/3 the rate of the disappearance of O2. It's 2/3 the rate of the disappearance of O2, isn't it? On 3, if you put in 0.1 and 0.1 for the molarities in the rate law, you get R. Well, R is clearly 0.01. So if you put in 0.4 and 0.05, we don't need a calculator. 40 times 5 is 200, but by doing that, we were cheating this decimal over 2 spots and this decimal over 2 spots, so the answer is 200. It's 4 decimal spots smaller than 200. It's 0.02, which actually is a doubling of R, so that's a 2 times increase for R over the previous R value. So we need to compare the change in molarities to the change in rate. If we go line 1 to 2, we lock down O2. The change cannot be from O2. This is a doubling. That's a doubling. So we get NO changed by a factor of 2. R rate changed by a factor of 2. What exponent is in the box? The exponent is 1. NO is a first order reactant. Line 2 and for O2, it gets a little bit more complicated. Let's use 2 and 3. So we need to compare the change in molarities to the change in rate. If we go line 1 to 2, we lock down O2. The change cannot be from O2. This is a doubling. That's a doubling. So we get NO changed by a factor of 2. R rate changed by a factor of 2. What exponent is in the box? The exponent is 1. NO is a first order reactant. Line 2 and for O2, it gets a little bit more complicated. Let's use 2 and 3. You could also use 1 and 3. But we have to get something where it changes for O2. So you can't go back to 1 and 2. I chose to go 2 and 3. So what happens for NO? It changes from 0.2 to 0.4. So it changes by a factor of 2. And we know that the exponent on NO is 1. So we have 2 to the 1 times the change in O2, which is 2 to some unknown exponent, and together with the correct exponent, they must make a rate that changed by a factor of 2. So this is 2 times 2 to the sum power equals 2. What's in the box? 0. Anything to the zero order is 1. So O2 is a zero order, and there's no point in writing it in the rate law. On number 5, what we want is the rate, but we have some really key information, and there's a couple tricks in here that they're really asking if you can do. So one of the things they're asking is, do you really understand what a rate order is? And if it's a zero order, what do you get? If the rate order is 0, then the exponent on the molarity is 0. That means that this effectively turns into 1. Anything to the 0 power is 1, and rate is k. So they're saying, do you realize that? And if we ask you for the k, do you realize you can find the rate and just say they're equal? If you find rate, you have k. And do you realize what a rate is? It's the amount used of the reactant over a certain amount of time. Often that's molarity per second. This time they have minutes, but that's fine. So what we need is the molarity of the reactant used up per time. So they told us it's 40 minutes, so the difference used in time is 40 minutes. I mean, they start at 0, right? So the difference is 40 minutes. Now, the extra little trick is how much of the ammonia is used up, because the rate is how much changes, right? It's a rate of change from reactant to product. So we need to know how much made the crossing of the arrow, how much is used up. Well, I don't know how much I ended with this. I know how much I started with, and you know what? That's not even the point. The point isn't how much you start with, it's how much is used up. And a key piece of information that I've got here is that it created 0.05 moles of N2. Also, I have the balanced reaction. So if one of these is created, 2 of these is used. So if 0.05 moles of N2 is created by a ratio of 2 to 1, 0.10 moles of NH3 was used up. So the rate, it's always based on the reactant, right, will be the change in molarity, how much was changed from the left to the right. 0.1 mole per 1 liter was used. How do I know it's a liter? They're all in one container. They're all gases. They fill the container. So the concentration is moles that I used per, in this case, 1 liter. So 0.1 moles per liter gives me molarity. The change in time is 40 minutes. I get 0.1 molarity per 40 minutes. Also, I don't get a calculator, remember, on the multiple choice, which is what we're sort of doing here. So calculator's banned in this section. So let's just do some mental math. And they really do think that you can manipulate some decimals, and you don't need to sit there with like second grade or something and multiply this out with a pencil. Let's say that 0.1 over 40 is essentially 10 over 40, which is 0.25. Now, when I say essentially, I mean it's close. It's an analog for it. But I cheated the decimal 2 spots bigger to make this 10, right? I have 1 spot, 2 spots. So the answer here isn't 0.25. That's 2 spots too large because I cheated the decimal too large. My real answer is 2 decimal spots smaller than what I just said. And remember, the units were molarity and minutes. So my rate is 0.0025 molarity per minute. On 6 and 7, this is almost just a memorization question. If you get ln of reactant plotted against time and you get a line, by the way the slope will be negative, you'll get that. But if you get a straight line, it's first order. And here's my mnemonic. I couldn't remember this for years. This looks like first number, one number, or one number. And therefore the exponent on the reactant in the rate equation is 1, and that means it's first order. On 6 and 7, this is almost just a memorization question. If you get ln of reactant plotted against time and you get a line, by the way the slope will be negative, you'll get that. But if you get a straight line, it's first order. And here's my mnemonic. I couldn't remember this for years. This looks like first number, one number, or one number. And therefore the exponent on the reactant in the rate equation is 1, and that means it's first order. Oh, look, it's a first order reaction. It has a straight line. What will the axes be? They'll be ln of the reactant versus time. What's the rate law for this? Well, let's see. What do we know? We know that a zero order continues at the same rate all the time, so the half-life gets less and less. A first order, by definition, and I would write this down, has a half-life that is constant. The half-life is constant, period, end of story. A first order reaction has a constant half-life. A second order reaction has a half-life that is getting longer and longer. Well, look, here's an even amount of time, at least good enough for our work. That's pretty much 10 seconds every time. And look, the amount of A reactant is reducing to half of the previous amount every time. That's a half, that's a half, that's a half. The half-life is constant. It's a first order reaction, and the rate will be Ka molarity to the first.